Hi, I recently made a project based on a research paper which identifies LLM fingerprints from ChatGPT, Claude, Gemini, DeepSeek, and Grok. I thought I'll record myself making this project because while implementing it, I learned a lot, and I think it could also help anybody who is wanting to learn. In this video, we'll talk about different techniques like LLM2Vec, low-rank adaptation adapters, contrastive learning, and specific problems that I faced while implementing this, like multi-GPU crashes, memory bottlenecks, precision errors. So it is going to be a very educational experience building this on video. So first, I'll show you the demo of what we are going to build. So this is the tool that we are going to build. You see, I'm waiting for Grok to complete a response and paste it on my tool. And my tool identifies that it is Grok with over 83% confidence. I paste the same query on Claude, paste it, and it finds out that it is Claude, this time with over 43% confidence. So this is the tool, and I posted this on Twitter. Hardly anybody noticed, except for David Yin, based on whose research we are going to build this project. So I'll quickly show you the research paper. This is the research paper, and here is the code associated. Mm. The major outcome from this research paper is that it conclusively proved that LLM outputs, the text, in fact have idiosyncratic patterns, which helps us identify which LLM produced a piece of text. They achieve 97% accuracy on handout validation data and 5-way classification problems, which involved ChatGPT, Claude, Grok, Gemini, and DeepSeek. This is a good research paper. So the mechanism is like this. You have a prompt, you pass the prompt to different chat APIs, get their responses, and then pass that responses through a neural network classifier, which identifies which piece of text was generated by which of the chat APIs. In this video, we are going to implement this neural network classifier and inference it. And this is the code which the researchers released. It is a very simple repository with three main files. One is the generate responses, which essentially generates all these different chat API responses by passing different prompts through these models. We have transform. The researchers wanted to be sure that their classifier is indeed studying the idiosyncratic patterns of different models. That is the reason they ensured to pass the input tokens through different kinds of transformations, like rephrasing, paraphrasing, shuffling some of the words, translating into a different language, and still, if the classifier is able to find out which was the original LLM which generated the text, then we can be very sure that our classifier is indeed finding idiosyncratic patterns in the LLM outputs. And then you have the classification file, which has the neural network classifier in it and the inference training code. But what are these different kinds of idiosyncratic patterns that you can find? This is my website, sayadaman.com. I usually post my projects here and I write blogs here. If you notice, the last three blogs are based on LLM fingerprinting. In this, let me just walk you through a small segment which talks about the different idiosyncratic patterns which exist and which our classifier will try to identify. Right? One is the lexical signatures. Different models have different lexical signatures. In simple terms, it is just overrepresentation of specific tokens. Like ChatGPT is more likely to use the term certainly as compared to other models. Then we have structural fingerprints, which is simply rigid formatting rules. For example, ChatGPT, when it returns a bullet point list, it is more likely to have its first item bold. Whereas for Claude, it does not bold any items, it's more simpler in its output. And in case of Llama models, you see a specific conclusion section at the end of the output. So this is a specific structural fingerprints, the formatting, which are unique to different models. And then there is the semantic tone, which models develop throughout their LLM training lifecycle. So there are three different phases that LLM training goes through. First is the pre-training phase, at the end of which we get the base model. Then we have a supervised fine-tuning phase where the model learns to respond to questions, to respond to instructions. And then you have reinforcement learning phase where the model is trained to follow specific policy and reward models. What happens is different model builders have different supervised fine-tuning stage and reinforcement learning stage. ChatGPT supervised fine-tuning stage, reinforcement learning stage could be distinct from Claude's supervised fine-tuning stage, reinforcement learning stage, could be distinct from Gemini's supervised fine-tuning stage, reinforcement learning stage. So by the end, the product that you are using via your ChatGPT app or your Gemini app or your Claude app, these different end products have gone through distinct supervised fine-tuning phases and reinforcement learning phases, due to which they developed different semantic tones. So these are the three different kinds of idiosyncratic patterns that we aim to find out: lexical signatures, structural fingerprints, and semantic tone. So we hope that our classifier, the neural network classifier that we are going to use, can identify these different idiosyncratic patterns, and with the help of that it can accurately output which specific piece of text was generated by which specific large language model. With that context set, let us proceed to get a GPU where we can actually implement this. In fact, before getting the GPU, let me show you the GitHub repo where this has been implemented by me. So this is the LLM Idiosyncrasies project. So this is the repo which has all the inference code for this demo video that I have shown you. So we'll implement a part of this repository in this video. So this repository I have made it specifically on Kaggle notebooks using P100 GPU, because it is interesting to run on limited compute and find out the specific production problems that you will face in trying to maximize the GPU utilization. So I have also written about the specific challenges I have faced while trying to replicate this on Kaggle notebooks, like multi-GPU crashes, memory bottlenecks, and precision errors. We will eventually go through this blog post as well while we are dealing with similar problems in this implementation. So this time, let's not rely on Kaggle notebooks, but let's take a instance of GPU from either RunPod or from Lambda Labs. Lambda Labs are quite popular, but for some reason they do not support payments from Indian based users. So let's default on to use RunPod for now. It is quite easy to set up RunPod. You come to pods and you notice they have clearly mentioned some of the popular featured GPUs here. We'll use A40, which is based on Ampere architecture. It gives you 48 GB video RAM and it gives you 48 GB of RAM with 9 virtual CPUs, which is quite enough for the model that we are trying to inference. The model we are trying to inference is about 16, 17 GB in total. So 48 GB of video RAM and RAM is enough for our use case here. I encourage you to also look at some other models, some other GPU hardware that is available here. You have H200 SXM, which is based on Hopper architecture. You have B200, Blackwell architecture based GPU. This is a very good GPU, which is mostly used in the industry for the latest inferences, clusters of B200. So it's also interesting to understand a bit about these different architectures. Like Ampere's architecture amputates the precision so that the range remains consistent, but the precision comes down. And in Hopper's architecture, which is a specific innovation for large language model training, here, large language model training or transformer based training, here, the architecture itself has the ability to intelligently find out which specific layer of the transformer or the model requires which precision level. If a particular layer is suitable to process with just 8 floating point 8, that layer uses floating point 8. If the next layer you needs brain float 16, it uses brain float 16 for that layer. And if there is a particular layer, for example an adapter, low rank adaptation adapter, which requires floating point 32, it uses floating point 32 for that specific layer. That is Hopper's architecture. And then you have Blackwell architecture, which maxed out the capacity, the size in which the chip can be built. So in Blackwell's architecture, you have multiple different chips which are connected to each other using NVLink. NVLink has the ability to transfer more than a terabyte in a single second. So the inter GPU communication is too fast that the CPU feels like this entire cluster of B200s is like a single GPU because the inter GPU communication is too fast. It is interesting to read about all these different architectures. And for now, let's stick to Ampere architecture based A40, which is enough for our use cases. So you can come down, and if you wish to have any extra container disk or volume disk, you can increase the capacity here. Let's just increase the capacity to 50 because we might load multiple models depending on which approach we want to take for inferencing. So let's just have little extra than what we would otherwise require. With this set, let's select on demand. You can also use spot, but it could be a little unstable because it can interrupt during your workloads. So I am going to stick with on demand for now. And then you just click on deploy on demand. And let us wait till we get the connection details for our instance. Once we have the connection details, we will SSH into this instance, inspect the instance for a bit, then open our cursor and work on that for the implementation. So we have the connection details here. I will use the SSH over expose TCP. So let me just open my cursor now, and in my cursor configuration, let me add this new. So this is the address that we are going to use. So I'm going to just change one of my previous instances, which is terminated currently. So I can just reuse the same one and update the creds there. All right, so that should be enough. Now that I have this specific SSH credential set, I can directly SSH into this. Let me open my terminal because that is a little easier and more convenient. Here I can just SSH into this new instance that we got. Yes, I proof connecting. Yeah, we have entered our newly allocated RunPod instance. So the first thing that I would like to do is just update, and I'll just install htop so that we can look at the state machine, and also install nvtop, which is a better version of nvidia-smi. All right, yes, continue. So we have our installations done. Let's just open htop and see the state. Okay, this is nice. We have about 96 cores available, out of which we might be able to use a few of these cores, and other users might be pinned to some of the cores. And these are the processes which are run by the user root, which is allotted to us. Currently, there are not a lot of processes here, which is on the expected lines. And we notice the uptime for this server is 2 days, which means the server is not very not very long running, which is a good thing. I've also noticed sometimes the number of uptime days were above 150 days as well. So looking at 2 days is reassuring. Let's also look at nvidia-smi. Okay, we have nvidia A40 as expected. Oh, we are at P8. We are not running any GPU workload, so that is okay. And the power utilization is low, which is again on expected lines because we are not running any GPU workloads as of now. And GPU utilization is 0%, which is on expected lines. So we are good to go with this. Let's just have a look at nvtop as well. Currently should just show a flat line, right? The GPU, memory, and the compute both are at 0, which is also on the expected lines. So our server that we got from RunPod seems to be good. Let's see the present working directory and if it has any specific files. Yeah. So let's just create a new directory where we can work. LLM Idiosyncrasies demo. Let's call the repository this. Then change directory to the repository. Here I'll just create a ipynb file inside of which we can work through our implementation. Right. I'll just exit from this SSH from my terminal, and I will SSH from my cursor. Okay, let me wait for the cursor to connect to this remote server. Okay. All right, we have entered the server. And if we open folder now, we should be able to see the directory that we made. This is the directory that we made, which is visible here. Let's open it. So we should be able to see IPYNB notebook here that we just created from our terminal session SSH. Right. So cursor is configuring all the ports as well from the remote server to our local. But right now we do not need this, but it's a good thing to have. Okay. So now let's get started with the implementation part. So first off, what we will do is we will install some of the key dependencies that would be required for us. But before that, let us select the kernel we are going to use here. So it will provide us with the kernel options. Right. We need a Python environment. Yeah, Python 3.11 is fine for us to work with. And let us get the installations done. If you notice, we are using transformers, parameter efficient fine tuning, huggingface hub, accelerate, save tensors, LLM2Vec, gradio, plotly, HF transfer. As we proceed through the video, I will also explain what each of these libraries are used for, what is the techniques that these let us implement, and also I'll try to explain the mathematical intuition behind some of these techniques and the research papers from which these techniques came into existence. Take a particular note of these specific versions that we are using: 4.44.2, 0.13.2, and for LLM2Vec 0.2.3. The reason I am specific about these versions of dependencies is that it is very easy to fall into version conflicts, dependency conflicts, and we struck in that zone for a long time if you're not being careful about this. For example, recently while I was using one of the models from Hugging Face, just want to show you the example for why this is important. This is one, but I have not changed a lot here, so I'll show you another example where this kind of uh, can give you a lot of problems. So let us just check here. So recently when I was using this specific model for one of the inference purposes, I looked at the commit history, and you notice that it was previously updated in May 2024. And then suddenly, this is December 2025. In December 2025, there are recent commits. And these recent commits has to do with the versions. And because I have just tested the new project in the past few days, I was occupied in a very severe dependency hell. And finally, I found out that these two commits are the reason for my agony and the pain that I have been through. So these kind of things happen, and so that you save your time, be very specific about these versions and use this. You can, if you're pretty sure that you will not fall into any of these dependency conflicts, then go ahead. But as a safe thing, I would recommend you to please use these. And then let's log into Hugging Face with our Hugging Face access token. The reason we would need to log in into Hugging Face is that we are going to use Llama model, and for the Llama model you need specific permission to use that Llama model. So that is the reason why we need access token. So I'm giving my access token here, and I have been authenticated with the access token. And now what I'm going to do is I'm going to load the specific model which the researchers have released, the researchers of LLM Idiosyncrasies paper. And I'm going to load the specific model with the weights in workspace / classifier chat. It is important that I use workspace because that is the persistent memory. That is the volume which is attached to our instance. Anything that is stored in workspace will be in a volume which is persistent. Whenever you restart your server, it will always be there. How do I know this? So if you look carefully, when we are on a RunPod, notice that we have attached a specific external volume. Let me just show you the edit option here. See, here it says you will lose all data that isn't stored in your volume mount path, which is / workspace. So it is useful that we store our important data in volume mount path, which is / workspace. And there is another reason why we would want to store this here. One reason is persistent memory for sure. And there is another reason. You don't want to overwhelm your disk space. You do not want to overwhelm your video RAM with things that can be put aside, right? It is not difficult to pull it directly from the volume, but it is very hazardous if you are storing it on your disk space and the disks get too full. Your instance could suffer. Intense utilization of the resources can constrain it, can cause a severe bottleneck, after which you will not be able to run even simple tasks like running a Jupyter notebook. Even the kernel would not start. You do not want to have those kind of problems, so it is always good to attach the loaded model to a different volume, the volume that is attached to your instance. So let me just download yida classifier chat on this volume. So now what is yida classifier chat? Let me just show you the specific collection. This is the yida's classifier chat. So we are downloading all these files from this one command that we have here. And all of these files we're downloading in the checkpoint path, which is workspace / classifier chat. So what are all these files? You have head.pt, you have model.safetensors. These two are the important ones that we will focus mostly on. So model.safetensors, you notice, is 15.2 GB, which means it has the base model, Llama model, which was used during this research work. And it also has the head. It has the entire model. Yeah. So here, as you can see, this has all the layers which correspond to a Llama model, 31 layers. And it also has the head at the end, which they attached and trained specifically so that it can classify which specific LLM model, ChatGPT, Claude, Gemini generated a piece of text. So this file has all the weights available for all the layers of the model, including the base Llama model. If you look closely, for example, look at the self-attention block. It also has the weights for the adapters. low rank adaptation adapter A, which is in floating point 32. You have all the low rank adaptation adapter attached here and with their weights available, which is a good thing that the researchers have released for us to make use of. And also, if you notice closely, this is an interesting point to understand. The original layers of the model are in brain float 16, whereas the low rank adaptation adapter segments are in floating point 32. The reason could be because brain float 16 compromises on some of the precision, while floating point 32 has higher precision. And both brain float 16 and floating point 32 have the same range that they can represent. Let me quickly show this to you with an image. Right? Let us look at this image here. So floating point 32 has 8 bits corresponding to the range and 23 bits corresponding to the precision. Similarly, brain float 16 also has 8 bits as its range, but only 7 bits for the precision. So brain float 16 essentially compromises some of the precision in favor of having sufficient range. This is a reasonable trade-off in large language models and neural network training in general, because precision is little less important as compared to the range that you will require for these training and inferences. If you think about how a neural network actually functions, it goes through a forward pass, and then based on specific errors, it back propagates and then moves forward with the optimizer. So it essentially just needs to know if the optimization has to be in a positive direction or a negative direction. So precision here is not the most important thing as compared to the range that you want to cover. So that is the reason we can safely adopt brain float 16. And this reduces the number of bits that you are using. So it is a benefit that you can maximize the utilization of your GPU hardware by using lesser number of bits. Previously, if you were to use 32 bits in the standard floating point 32, here you are just using 16 bits. There have been further innovations where only 6 or 8 bits are also capable of being used. But for now, let's stick to brain float 16 and floating point 32. So back to the model that we are loading. These are the essentials to know about the model. We can also look at the shape of the different layers here. And the number of dimensions are 4096, which is common for many of the Llama models. As you proceed, you'll be able to see the different rank values which are used for low rank adaptation adapters as well. And for the specific head, the normalized final is 4096, and then that goes to the linear layer, which has 5 classes configured. These 5 classes correspond to the 5 classes of the LLM models, which are ChatGPT, Claude, Gemini, Grok, and DeepSeek. So we are downloading these specific weights via this command. So we have successfully downloaded it with this command now. Now that we have this, let's begin. Now that we have this, let us begin building our model, the classifier that we are going to use. So before we get a classifier to build, let us make some essential imports that will be useful as we proceed. And let us also set the specific paths that are important, like the checkpoint path, so that we can load the weights of the models that we have just downloaded. And if there is any offload to be done to the disk, which specific folder you want the offload to be done on. Once we have these considerations taken into account, let us begin implementing our model, right? Let's start with having load classifier as the name, and the checkpointing path is the checkpoint path where we have stored all of the downloaded model, which is workspace classifier chat. Okay. Once we have this done, first thing is to start with a clean slate, because you do not want any kind of memory issues to happen later on. So you are starting with clearing everything out. And once we have cleared everything out, the next thing is essentially we have to specify what the base model we want to use here. Okay. So the base model that we're using here, if you notice, is LLM2Vec Meta Llama 3 8 billion instruction tuned mass next token prediction model. Now, what exactly is this model? Let me just quickly show you. So this is the model for which we have also got the licensing, and our access token for Hugging Face that we have provided gives us the license to access this model. So here you see you have all the specifics required to load this specific instruction tune mass next token prediction model, which is an LLM2Vec. So now a bunch of questions. What is LLM2Vec? What is instruction tuning? What is masked next token prediction? I will get to all of these as we proceed forward. For now, let's just know that this is the base model that we are going to use. Now, once you have the base model, I also want to explicitly specify that offload path exists, right? So if at all there is anything that has to be moved to the disk, you have to have the specific location where you want it to be at. Now, once that is done, the next step is to get the tokenizer ready for us, right? And this tokenizer is for the base model ID, which is the repo that I just huggingface repo that I just showed you, which is LLM2Vec Meta Llama 3 8 billion parameters model with instruction tuning and masked next token prediction. I'll explain what each of these terminology means as we proceed forward. Okay, once we have the tokenizer set for that specific model, the next step that we are interested to do is load the model itself. Right, you want to load the model, and for loading the model, you can directly use the Hugging Face auto model. Then from pre-trained, you are using the base model ID. Right, you are giving the brain float 16. As I told you, the reasoning is it uses the same consistent range and has lesser precision, which is okay for large language model based setups. And then we are mapping the device to CUDA. We are loading this model directly on our GPU. We do not want to load it on our CPU and then move it to GPU. That would just be an additional memory bottleneck. We do not want that. And then you have the offload folder. If at all the GPU is filled up, it goes to the RAM on CPU side. And even if that is filled, then it goes to the offload path, which is on the disk. And then you are ensuring that low CPU mem is usage is there, and the token which we have provided for the Hugging Face, that is here. And once you have the model loaded, you want to ensure that no unwanted memory or anything is left. So right after that, let us just clear everything. If any leftover things are could be present as a reminiscent, we'll just clean that up. So far, if you notice, we have just selected the base model that we want, and then we have got the tokenizer for that base model, and then we loaded the base model, right? And also you understand the specifics about brainfloat 16, about device mapping to GPU, directly loading in video RAM as opposed to CPU RAM and then moving it to video RAM. That would be bottleneck heavy. And then offload folder, the specific path on the disk where you want to store it, and you're just cleaning any leftovers, so that the clean slate is important. You don't want to have any memory or cache remnants causing errors or issues as we move ahead. So far this is what we have done, and then moving forward, let us take the specific path where our this cursor is getting too excited and writing it by itself. All right, so we have the checkpoint file where we want the specific model.save tensors that we downloaded from yida's classifier chat, which the researchers have released. Yida is name of one of the researcher, David Yin, goes by the name Yida Yin, as per the research paper that we have just seen. Yida Yin. This is the same Yida here, who's one of the researchers who have released this specific model. So this model.save tensors, which I have loaded in our workspace, we are specifically giving that address to our checkpoint file here. And once you have given that specific file, but why are we giving the address for this specific file, right? It is just so that we can load all of these model weights that we got from either into the base model that we have here. So indentation is not correct here. Okay, this is the correct indentation. So now we use the specific checkpoint file. From the checkpoint file is this, right? Checkpoint path is this. In our workspace, persistent memory, at this specific classifier chat location, we have all these files downloaded. So from that specific checkpoint file, we are loading the checkpoint file in a state dict, and we are loading it on our GPU directly. Again, we don't want to go via CPU and then go to the video RAM. We don't want to go via RAM to video RAM. That would cause a lot of bottleneck. We're directly loading it on our video RAM. And once we have that base model, which is the base model that we got here, the Llama TB instruct MNTP model. In this base model, we are loading the weights that we got from this checkpoint file, which is the location where model.save tensors from yida's released model is stored. So once we have this here, we just do not want any lingering state dicts, and we are just explicitly clearing the state dict, and then we are ensuring no caches or memory remnants are there. And then if all of this is successful, you are just printing that we have directly loaded this to GPU. And if at all the checkpoint file is not available, then you just use the base model. You do not load the weights from the checkpoint file. Okay. Now, once we have the checkpoint file and all of this ready, The next thing that we're going to do is we are going to convert this model that we have, the model which, again, cursor is getting too excited and writing things by its own. All right. So the model that we have got so far, which is just a quick recap, is this is the base model that we had, LLM2Vec Meta Llama 3 8 billion instruction tuned mass next token prediction. And for this specific model, we have loaded the weights from the downloaded location, which holds the weights that yida, the researcher, have released with respect to their LLM idiosyncrasies research, based on the specific trainings that they have done to train the classifier. So we have loaded those specific weights on our loaded model from Llama 3 8 billion, and we ensured that everything is clear, static and all, and then we are converting this model into LLM2Vec model. All right. So what is LLM2Vec model? And what is mean pooling means here? Why is there pooling mode mean? And what is max length 512? So these are the questions that I will just answer in a bit. Before that, I just want you to give a rough flow about what is going to happen. Right, then you're finding the hidden size, which is from this model. What is the hidden size? And once you know what is the hidden size from that, when you get it, you are directly attaching a head to this model, to this LLM2Vec model that you have. You find out the final layer's size, and once you know the final layer's size, you can attach a linear classifying layer to that, which is just a linear layer, which starts from hidden size, which is the final layer of the LLM2Vec model here, and then that is projecting onto number of labels. Here the number of labels are 5, corresponding to ChatGPT, Claude, Gemini, DeepSeek and Grok, and that is stored as an attribute of model. All right, so once we have loaded the head, the next important thing is we have to load the weights on this head as well, which yida has provided with. And unless you have the weights for this specific head loaded, the classifier head that you have, it does not have the original weights. So that is the reason why we are specifically passing the address where your head is stored, which is again the checkpoint path where we have downloaded yida's model, and the specific head.pt, which is this head.pt. All this, which is 42.4 kb, this will get downloaded, right? And we are using the target to be on GPU. Again, directly on the GPU we are loading this, which is the same where all the model weights are also available in our video RAM. And then for this head, which was in this line, the head was randomly initialized, random initialization of weights. But those weights are not what are required to us. We require the weights which we got after training from yida's model. So in this line, we essentially load the head in the model with the head.pt that we get from yida's trained model. And this is on the target device, which has to be the directly on GPU video RAM, right? So once you load the model head with the trained weights of head from yida's classifier model, we just ensure that it is on our target device. This is important that all the layers are on the same device to avoid a common issue that people fall into, which is some of the tensors are on a different device and some of the tensors of a different layer are on a different device. So because the device mismatch, multi GPU crashes, or it does not have all the requirements on a single device, so it can cause a lot of unexpected weird bugs. So just to ensure we don't fall into any of such bugs, we explicitly ensure that it is on the same target device. Now, once that is done, we want to get our model evals set properly. So we don't want to be in a training mode right now, right? We do not want the backpropagation, the gradient computation, the optimization, all of these neural network mechanisms. We don't want to run this because we just want to run the inference right now. So once we have that, we are going to just clear any of the leftovers data, and then you can essentially just return the model and just return the model here. Okay, so I can just quickly run you through what exactly we have done here once again. So we have just specified the checkpoint path where yida's classifier model, all the files are loaded on our persistent memory, the volume that we got from our RunPod specific volume. If I edit it, can show that this is the volume mount path slash workspace. So we stored everything there, and we also showed our offload path to be on the persistent memory instead of being on the disk, where overconsumption of disk can cause suffering for the server and any of the workloads will not work properly. And then we begin to load the classifier. At the end of this, we will return the actual model which is required for us to run the inference. Okay, so first we clear some of this, and then we have the base model, and to the base model you load the tokenizer corresponding to the base model, and then you load the base model itself. You ensure that it is in brain 16 and the device you are using to load this is directly on the video RAM of the GPU. That offloading path you give, and then you, once you have the base model loaded, you ensure that the weights in the base model are loaded from the classifier that was trained by yida. From this model, the weights, whatever the weights are here, you want to ensure that these specific weights are loaded onto the base model here. So once you have loaded all the base model weights, you convert that model into LLM2Vec. You convert that model into LLM2Vec specifically with mean pooling and max length of 512. All right, then you find out what is the hidden size of the final layer so that you can attach the classifier head to the base model, right? The classifier head is just a linear layer which has input dimensions to be equal to the output dimensions of the last previous layer. And then it has number of labels corresponding to 5 here. Each of the classes represent one of the LLM models required to classify, which is ChatGPT, Claude, Gemini, DeepSeek, and Grok. And then you ensure that the data types are brain 16 to ensure that our hardware utilization is sufficiently utilized. And once you have your head, you know that this is randomly initialized. The weights in this head are random initialization, and those weights do not mean anything to us. So we ensure that the head weights are loaded directly from the yida's classifier. The weights in this has to be loaded on our head, right? So the head attribute of the model loads the weights from head file, and we ensure that everything is on the same device, which is on our video RAM on GPU 0. And once you have it, you get your model ready. You want to ensure that the model is in eval mode, and then you return the model. That's it. Now, as promised, I want to explain to you what LLM2Vec is and what exactly this base model mean, which is LLM2Vec, instruction tuned, and masked next token prediction. All right, I'll get to both of that, but first let us ensure that the model can load. All right, that ran as expected. And once we have that, we want to load the model so that we can actually inference it. So in this line, I just want to load the model. So loading of the model can take some time. Let's ensure if it is actually being, some reason it shows it is in the pending state. Transfer migrated, migrating old cache. So this is expected to take some time. For some reason, the cell does not seem to be running yet. Why could that be? Let us just quickly check if the capacity is sufficient. You see, pod volume is consumed for 15.5 GB, which is expected because it has loaded our yida's model on our pod volume. And disk usage is 1.5 GB has been consumed, which is also on the expected lines. Memory consumption is not much, and CPU utilization is also below any hazardous situation. Okay, so why is this not loading? Did we do anything wrong? Let me just ensure if everything is fine here. We have loaded our tokenizer correctly. We have our base model, and then we have our garbage collector to clean everything up. Then you have your checkpoint file. So you have your checkpoint file. You ensure that you have your everything loaded correctly, and then you're converting that to LLM2Vec. Then you're finding out what your hidden size is. Then in your model head you are loading the hidden size, and you have your head file. Some path exists as there. Then model in the eval mode, you are clearing everything and you are returning the model. Is this broken? Then just load the classifier here itself. Okay, let's just interrupt this for a moment and restart the kernel and see if everything is fine actually. Now the kernel restart is also taking a lot of time, which indicates that the server health is not very good, which is not a very good indication. Let us just enter the server from our terminal and try to see if everything is all right. On htop, we are noticing considerable power consumption by some of the tasks running on server. Just do F6 and see the memory consumption. Okay, nothing alarming here. Everything seems to be right. Let's quickly see the parent relationship using function 5. So there is a Docker init process. What is it? Okay. So we are inside of a Docker container on this specific server. And there is cursor running here. There is Python process. These are the Python kernel that is running here. So this seems to be some kind of constraint happening here. Not able to pinpoint on what exactly is wrong. This is currently running. What exactly is running? There is only one current thread which is running, which is not a very good indication because the kernel restart itself is hanging. See, I'm recording this live, so these kind of surprises when they arise, I have to just deal with them right here. Let me check my nvtop, see if there is any abnormality here. Okay, everything seems normal. I cannot find any anomaly because the GPU usage percentage is 0. Memory also seems to be reasonably consumed, and the device 0 peripheral component interconnect express. Okay, the health seems to be okay in general. Nvidia-smi. Just watch Nvidia-smi for some. Watch. 2.5. So this looks absolutely normal. No indication of any overload or constraint at all. So what exactly is happening which is preventing even the restart of our kernel? Once again, if I notice utilization, video RAM utilization, we loaded some of the things here, but do not seem to have loaded on a video RAM successfully. So we have done some mistake somewhere, which I'm not sure right now. All right, what I'm going to do is I'm just going to close this for a moment, then freshly open it and see if we can get it running. What could have gone wrong? Gone wrong? Everything seems to be decent enough. We clearly are doing something wrong. So let me just run this once again. Dependencies are installed. Let me just restart it. The kernel. All right, successfully restarted the kernel. Once the kernel restart is done, just want to pass my huggingface credentials into this. Let me think if something has gone wrong so far. It doesn't seem like anything is going wrong. Just come here and see if I can just place my access token. I got authenticated, right? So I have authenticated myself. I'm going to ensure that checkpoint path is intact. I'm going to remove the existing model Then I'll specifically add a few print statements here. Okay, and I'll just download it once again. And now I just want to see if this works. I have my checkpoint path set. I have removed the currently existing model at checkpoint path, and let us just have these comments explicitly so that we do not go wrong anywhere. Okay, let me just run this and see if it is running, downloading the model 15 GB, everything. Okay, so here's the model is being downloaded clearly. Really, so far, I don't think anything wrong has happened to constrain our system resources. Seem to be on the right path so far. Now let us just wait for this to happen carefully. I really want to walk you through these specific things: what LLM2Vec, instruction tuning, mass next token prediction mean, and what is LLM2Vec mean pooling here, and max length 512. I will clearly walk you through that, but let us just solve this problem at hand first. Well, you're coding this live and recording when these kind of things happen. I want to be very open about these kind of problems so that anybody out there building, they don't feel vulnerable. This is common experience. These are common hazards that you face, and you have to just push your way through them. So this will take some time. This will definitely take some time. Meanwhile, let me think about what should I do next to ensure that any of the problems don't come up. So I think I should have a clearing of the cache after this. So all Hugging Face cache will be cleared from this piece of code. So as soon as this is loaded, I want to clear up all the cache and any unwanted things which are persistently sticking around. And once that is cleared, I will load my classifier model. And once the classifier model begins to load, I will actually move on and explain to you about LLM2Vec, instruction tuning, mass next token prediction, mean pooling, max length. So let us wait for this for a bit. It is closing to completion. All right, we see the comment which is model saved to persistent volume. All right, at the checkpoint path. So it is confirmed that it is present there. Now let us just clear the all Hugging Face cache for this model and then immediately run the load classifier. All right, now it is loading. Okay, so maybe we should just be a little bit careful about cache and everything. Okay, so now while the model is being loaded, we can, yeah, let's just confirm that it is actually being loaded properly. All right, seems to happen. Okay, that is cool. So it is proceeding as expected. So yeah, let's come to this part. what exactly does LLM2Vec, Llama, and all of this mean. Okay, so I'll tell you what LLM2Vec essentially means here. Okay, LLM2Vec. Let me just pull up the research paper, which is a very good research paper. But if you directly try reading this research paper, it might get a little overwhelming if you're not already spent some amount of time in LLM space. So LLMs, large language models, are decoder only models whose only job is to predict the next token, right? So even if there are 100 input tokens, at the output there is only just one token, which is the next token. It is the next token predictor. Large language models are next token predictors. We want to convert this large language model, which is a next token predictor, into an encoder model, from a decoder model to an encoder model. So once we convert this into an encoder model, what happens is that 100 input tokens which they are incoming, at the output you will have 100 embeddings corresponding to each of these 100 input tokens, and these embeddings will capture rich semantic meaning of each of these tokens with respect to all the other 99 tokens in context. Okay, so each of these token has to have rich embeddings so that we can use it for useful purposes. We have very rich embedding and rich understanding of each token with respect to all of the input space, right? So LLM2Vec, which is the decoder only model, which is LLM, you want to convert that into an encoder, which is a vector based space with this embeddings outputting for each of the input tokens, right? So that is the main objective of LLM2Vec. And how does it achieve this objective? Let me just tell you by walking through the paper here. First, you want to enable bidirectional attention. So in large language models, it is unidirectional attention. All right. So all the input tokens that you have, if they are in a sequence, then the future tokens from ith token will be masked so that they become zero. They are zeroed out. So your large language model can only look at the past tokens and learn the patterns in these past tokens to predict the next token, right? So this is a unidirectional attention. All the past tokens are visible to the language model to predict the next token, which is the ith token. So if I can quickly LLM unidirectional attention. Okay. So let us see if we can just get a quick diagram to represent this. So this is the actual transformers paper, right? So this section corresponds to the decoder only model, and this section corresponds to the encoder as well. But I want to specifically show you that only past tokens are visible. All right, this seems to be like a good visual representation here, right? So here for self-attention to happen, it is only looking at the past tokens and only weight 0, weight 1, weight 2, weight 3. And then this is the current token iteration that we have. Then any of the future tokens are not visible, which are zero down completely. Okay, that is the unidirectional decoder only models. And once you come here, you want to convert that into bidirectional attention, where it can also look at the future tokens. Okay, so that is what we mean by enabling bidirectional attention here. And once you enable the bidirectional attention, so the model is able to look at the future tokens as well. But during the training phase, the model has never known what to do with the future tokens. It has never seen in future tokens. It doesn't know what to do with the future tokens. So even if you're unmasking the future tokens, the model may in fact risk collapsing because it has never learned to see the future tokens and do anything with it. It does not know what to do with the future tokens. So to combat that problem of the large language model or the decoder only model not knowing what to do with the future tokens which are newly unmasked, we pass a small high quality data set for the training, so that the large language model's objective still remains to predict the next token. But this time it can look at the past tokens and the future tokens. Based on the complete past and future tokens, except for the ith token which is masked, it should predict the ith token. All right, the language model can now look at all the past tokens to ith token to predict the next token, which is the ith token, and can also look at all the future tokens of ith token. So now when you run it for some time on this new future tokens visibility paradigm, which is freshly opened up for them after unmasking the future tokens, the language model eventually tries to understand, oh, I need to still find out the next token, but this time I can look at the past as well as the future tokens. Self-attention takes care that the attention is computed properly for the past and the future tokens. And based on that, the ith token, which is the next token prediction, which the large language models are known to be very good at, it is predicted. Okay, so first is you enabling bidirectional attention. Then we are ensuring that the future tokens usage is learned by the language model. So we ensure that it goes through masked next token prediction. And then there is a phase called unsupervised contrastive learning. So now that masked next token prediction is done, the language model knows to predict the next token based on future as well as the past tokens, right? So what it has been empirically observed is that the embeddings which form after masked next token prediction, these are concentrated too close to each other so that the semantic similarity seems to be too high. The cosine similarity that you want to find out is not distinct enough to clearly separate out different tokens. We call it like a cone concentration of the embeddings in the output. Okay, which is not good. We don't want a cone kind of concentration. We want a more spherical kind of concentration where all the different embedding vectors have good distinctions between them so that we clearly know which vector is distinct from which other vector. Okay, to combat this cone kind of concentration, we use contrastive learning. Let me also try to just grab a contrastive learning cone versus sphere. All right, so here let's find a good diagram. Okay, this seems to be a good diagram here. There's a cone. Yeah, this is a much better diagram. Yeah, so here as you can see, the concentration is closer, right? Then you want to expand this further so that a spherical shape distribution of the embeddings can be observed. Conical is too concentrated. You want to make it spherical so that the distinction between cosine similarity is very clearly visible. Even this is a good representation of the distribution here, though this is for some other use case. Yeah, contrastive learning is a good enough, decent enough field in itself, but specific to language models, we want to understand it now. All right. Yeah, so these are some of the diagrams based off of which we can understand what contrastive learning means here. So here you have unsupervised contrastive learning. Okay, and so for language models, how exactly contrastive learning happens? That is a question, right? I will address that in a bit. Before that, let me just walk you through this paper and just try to capture and understand, pick some of the key terminology and the methodologies that are used in LLM2Vec. As I told, enabling bidirectional attention, masked next token prediction, and then unsupervised contrastive learning. And there are a lot of good evaluations done on this. So here you see there are a bunch of different ways here. So here, what you're saying here is sim CSC is contrastive learning on sentence embeddings. I'll exactly get to how this is computed in language models. Meanwhile, look at this Meta Llama 3.8 billion. This is the exact model that we are using in our training here as well, in our inference as well. So here, if you see LLM2Vec, the performance is quite good, right? So yeah, these are some of the things that I want to show. Look at these figures as well. The cosine similarity at different token positions at layers when comparing representation constructed with causal attention to those constructed with bidirectional attention, right? So causal attention is what large language models have. They cannot look at the future tokens, and bidirectional attention is what encoders have, which can look at the past and future tokens. All right, these are the cosine similarities at different token positions. And for bidirectional attention, if you notice, you are noticing it without training, which means there is no contrastive learning on sentence embeddings yet. So this is like a very weird and non-ideal distribution. We cannot really understand a lot from this cosine similarity, right? Later, when we pass it through contrastive learning on sentence embeddings, it becomes better, right? So this was the, let's just read to the conclusion of this paper. We present LLM2Vec, a strong unsupervised approach to transform any decoder-only large language models into a universal text embedder, which are encoders, okay? We perform an extensive evaluation on word and sequence level tasks and demonstrate the effectiveness of LLM2Vec in both unsupervised and supervised settings. Applying LLM2Vec to Mistral 7b. Okay, you have to know that LLM2Vec can be applied to any of the large language models. We are applying it to Meta Llama 3.8 billion. That is just a matter of chance and the capacity of your hardware. You can use any bigger model than that or a smaller model than that based on the use case. LLM2Vec is consistently applied on any of the models, any of the large language models. So here they are saying applying LLM2Vec to Mistral 7b achieves a new state-of-the-art performance on MTEB among unsupervised approaches. All right. So this is a way to measure the quality of embeddings generated. Okay. When combining LLM2Vec with supervised contrastive fine-tuning, this is the important part. When combining LLM2Vec with supervised contrastive fine-tuning, which is the contrastive learning pace that I'm going to tell you about next, Meta Llama 3.8 billion achieves state-of-the-art performance among approaches that train only on publicly available data. As of May 24, 2024. Beyond our strong empirical contribution, we provide an extensive analysis of how LLM2Vec impacts the underlying model and reveals an intriguing property of Mistral 7b, which explains its strong out-of-the-box performance with bidirectional attention. Okay, that is a good thing to know. The simplicity of our approach, as well as its compute and sample efficiency, makes LLM2Vec a promising solution for low resource and compute constrained scenarios and opens up several interesting avenues for future work. All right. So I'll just open my website once where I have written about this. This is the website where I usually post all of my projects and have detailed documentation for everything that I do. In the writing section, in the part 2 of my LLM fingerprinting post, let me just walk you through the LLM 2Vec section. So what I'm explaining is decoders output one next token per iteration, while encoders output 100 rich embedding capturing full context, right? So yeah, you see, for the decoder only model, you have 100 token as input, and then you have 101st token as output, which is the next token prediction. But for encoder models, for LLM2Vec, if you have 100 tokens as input, you will have 100 embeddings as output, and each of these embeddings corresponds to one of the tokens, right? So you have rich embeddings, one per token, and this is in context to all the other 99 tokens. Okay. So this conversion from this next token prediction to this rich embedding is very fantastic. And why is it so? Why do we even want to convert a decoder only model like a large language model into an encoder model, which can have rich embeddings? Why do you even want to do that? Right? You know that LLMs have in a way brought about the AI hype that is currently undergoing. It is because LLMs got too good at what they are meant to do, right? So while they are trying to predict the next token prediction, they have very rich contextual understanding of each of the tokens just from looking at the past tokens. They have rich semantic understanding, semantic meaning of those tokens based on which they are able to predict what the next token should be, right? So these large language models intrinsically have a lot of information about the tokens. So if we are able to harness this internal intrinsic knowledge of large language models with respect to all the tokens that they have the information about and turn that into a richer, semantically sound representation, then that will be extremely valuable, right? So just let me just zoom in on this specific paragraph that I have written. The Llama model already has so much intrinsic knowledge stored in its weights about words to predict the next token. When this is turned into an encoded model, this rich intrinsic knowledge is intact, and we get additional knowledge about each token with respect to all other tokens. It becomes excellent at capturing the meaning of a token in context to the entire input, right? And it is not surprising that this LLM2Vec model consistently outperforms the traditional architectures like BERT model, Robota model, which have been into existence for quite some time and even to this day. But LLM2Vec changes the game completely because they consistently outperform these models. And also, you can expect that a smaller model like GPT-2, whose LLM2Vec is generated, could be a little less effective than LLM2Vec for a bigger model like Llama 38 billion. And for a bigger model like Llama 370 billion parameters, LLM2Vec could be even more effective, right? So that is on expected lines. So that is the reason why we even care about converting a large language model to an encoder. Okay, and how exactly is that done? Once again, a quick grasp of ideas here. You want, these are all the future tokens marked by X which are masked. Okay, the model is not able to look at any of the future tokens. So we have to unmask these future tokens. So now all of the future tokens are also visible for the model. Okay, that we are doing is unmasking future tokens enables bidirectional attention but risks model collapse without masked next token prediction training. All right, so first step is clear. All the tokens are masked. You are unmasking all the future tokens. And once the future tokens are unmasked, because the model does not know what to do with the future tokens, you train masked next token prediction. All right, that is exactly what I explained here. First, you are doing unmask the future tokens to enable bidirectional attention. Then the decoder only model has never learned how to use the future tokens. So the model risks collapse. So here we apply masked next token prediction, which means the model will still try to generate the next token, but now it can see the past and future tokens both. It now generates the next token with a complete context of the entire input. Exactly. Right? We can train the model to use its newfound superpower, the new superpower being looking at the future tokens, to see the future tokens by just telling it to predict the next token by looking at all the past and future tokens. We can train the base model with bidirectional attention on some high quality dataset so that it learns to use future tokens. But training on entire 8 billion model again with bidirectional attention can get prohibitive. right? So we use low rank adaptation here. I'll tell you what low rank adaptation is and why exactly we use. But now that you are clear with the first phase, which is bidirectional attention, you have to enable, and then you have to run it through mask next token prediction. Then you go for the contrastive learning phase, right? So here, so contrastive learning, so this is the before contrastive learning, it is like in a conical shape. The distribution of the embeddings are not very distinct, right? So after undergoing contrastive learning, it gets spread out. It becomes, the distribution represents closer to a sphere with evenly distributed distances. So now you can very clearly know that, okay, this embedding is quite distinct from this embedding, right? Earlier, you cannot say this embedding, the concept of cosine similarity itself is very much fragile here. But here, you can actually find the distinctness. But how exactly are we able to do this contrastive learning on language models, right? It is so simple. The mechanism is so simple that it almost feels obvious, right? So the thing is, you just apply higher dropout to the layers in the language model, right? So you have a set of incoming tokens that represent a sentence, and you're adding higher dropout at different layers. So the weights are turned off at different layers at a higher rate throughout this language model. So the final embedding that is generated will slightly differ for each of the input token for the same sentence, right? If this is slightly differing, if the same embedding which ideal in an ideal world should represent, because of higher dropout, slightly different embeddings are generated here. So because these slightly different embeddings are generated, the much differing embeddings eventually spread out. Because if these two are too similar, they should have some cosine similarity between them. And if these slightly different ones are closer in cosine similarity, the ones which are not this close, they will eventually be spread out to have higher cosine, right? So that is the entire logic behind just adding higher dropout and letting the contrastive learning take place. All right, that is how we just spread the cone to form a sphere. Okay. So this is a good blog post. So I would highly recommend you just go to sayadaman.com, go to my writing section, read about this thing. And even after reading this, if there are any loose ends or any understanding gaps that you feel, I would be more than happy if you just reach out to me on Twitter saying, I have watched your video, I have read through your blog post, and there is something that I want to understand directly from you. I'll be so much happy to hop on a call and talk to you. Yeah. So yeah, that's it. That is LLM2Vec. And I'll also explain to you what low rank adaptation means. I'll get to it a little bit later as we move ahead with our video, right? So now back here. So if you see, now this will begin to make sense to you, right? Now this model is LLM2Vec model, which I've essentially converted a decoder only model into an encoder. This LLM2Vec was applied on Meta Llama 3 8 billion model, which was instruction tuned. Instruction tuned is essentially, it is not just a base model, but it has been fine tuned so that it can respond to instruction and answer to questions, right? Before the instruction tuning, it will just try to complete the sentence. But after instruction tuning, it knows that it has to respond to questions with answers and respond to instructions with reasonable responses, right? And then it is mask next token prediction. Okay, so we are using a model which has already undergone mask next token prediction, because as you can assume, mask next token prediction could be compute intensive. We do not want to do that on our hardware ourselves, because for 8 billion parameter model, if you are trying to train that on a new data set by enabling it to look at the future tokens as well as the past tokens, for the purpose of mask next token prediction, that will become intensive for us, right? So that is the reason we are directly using this model, which was already mask next token prediction have been implemented on this already. Instruction tuning have been implemented on this already. And this is a Meta Llama 3 8 billion model based on which this LLM2Vec has been processed. This is the base model that we are using. So once this makes sense, let me just proceed down to the other line. This, right? So here, what we essentially do is once we got our base model and once we loaded the base model with the weights that we got from the research papers trained model, we convert that into LLM2Vec, right? This is the base model which is being converted to LLM2Vec. This is the tokenizer that is required, and we are saying we want to do mean pooling here, right? What does this pooling mode mean, right? So once this LLM2Vec is converted from LLM2Vec to an encoder model, as I mentioned, the number of input tokens, how much ever you send it, same number of output embeddings will be generated, each embedding representing the input token. So this can be, the size can be varied, right? The size is not consistent, it is dependent on the input, but we want the size to be consistent at the output layer so that you can attach a classifier head. You can attach a linear layer which will act as a classification head for determining the 5 classes that we care about, which are ChatGPT, Claude, Gemini, DeepSeek, and Grok. All right. So to attach this classification head, the final layer of the LLM2Vec has to be consistent in its shape. So to ensure that this consistency of the shape at the output layer, we apply pooling. And in this specific case, we apply mean pooling. Okay. So let me just again plug back to my blog post. See, read this. Mean pooling averages 512 token embeddings into a single 4096 dimensional vector, which is being feed linear classifier outputting 5 classes, right? So now look at this specific diagram here. You have some input text. Okay, this input text is passing through Llama 8 billion instruction tuned model, which has bidirectional attention, unmasking done, which has mask next token prediction, which has contrastive learning. And then the output from this model will be of the shape batch, sequence length, and 4096. Right? So if there is, think of batch like the specific sentences. If there are 10 sentences, let's just say that there are 10 batches. Right? Sequence length, assume that to be the length of one sentence, right? The number of tokens. Let's just say there are 512 tokens. We want to cap it at 512 tokens. It could be less than 512 tokens, but we want to cap it at 512 tokens. And then you have the dimensions, what each of these individual tokens represent is captured in these 4096 dimensional vector. So this is the output that we get from Llama 8 billion instruction tuned model. Okay, now we want to pass this through a mean pooling layer. Okay, when you pass this through a mean pooling layer, this will essentially try to nullify the sequence length, the 512. It will try to pool the sequence length by using mean pooling so that the shape after mean pooling becomes whatever the batch size is, batch comma the number of dimensions. So every batch will have specific 4096 dimensions. So this means if one batch represents one sentence, then one sentence has one specific feature dimension vectors, which are 4096 dimensional vector for one specific batch corresponding to one specific sentence, right? We want to standardize this output from average pooling so that this can be plugged directly into our linear classifier. So from 4096 dimensional feature vector, you want to map that to just 5 classes. And these 5 classes correspond to the large language models that we want to classify. Just to ensure this transition can happen, this linear classifier can be attached reliably to the base model which has been converted into LLM2Vec. We ensure that the output dimensions are consistent so that the linear classifier can be attached to this consistent outputs. And once it passes through the linear classifier, you apply softmax to whatever the output comes. And softmax is a very simple mathematical function which takes all the numbers, and if all the numbers are added to 1, then what is the contribution of each of the individual number to all of that one. If you're not familiar with softmax, I'll just show you the uh, softmax. Yeah, like that. So if there are some set of numbers, once they pass through our softmax activation, they become probabilities, right? So that is just your just summation for the exponents of all of these numbers by what the contribution of each of the number is to it. So that gets us the probabilities. Once you add all of these probabilities, it becomes 1, right? So that is a softmax function, which is like a fundamental function used in neural networks and deep learning at the final layer. So yeah, so that is the reason why mean pilling is applied. It finds the mean of all the individual ones. Okay. So here I have not yet told you what low rank adaptation adapters are. I'll get to that right now. Okay. So as I told you, once the bidirectional attention is enabled, that also the future tokens are being visible. So what happens is the model does not know what to do with the future tokens. So you have to train some high quality data set to pass through this so that the model learns to use also the future tokens. But training a 8 billion parameter model is very resource intensive, compute intensive, and it is uh, also costly, right? So we do not want to train all of those 8 billion parameters. We want to be smart about this. We want to use a smart way of training it for our specific use case, right? That is where low rank adaptation adapters come into play. Just show you a low rank adaptation. Right? So what is exactly low rank adaptation? What is LoRA in short that we call it? LoRA, low rank adaptation. So this is a very simple idea, but like very effective idea. So for all the layers that you have in your language model or any transformer based model, we select specific layers. Okay, for transformer models, we usually select mm, layers which are in the attention block, like which correspond to the query vector, projection vector, and which correspond to the query projections, key projections, and value projections. So these specific aspects, we modify the internals of that, of the specific layers, so that the entire architecture, all the layers are frozen. And these specific layers, like the query, value, and key, these have a parallel pathway going through them. Okay, which essentially is one pathway is the pre-trained weights which are frozen, and then there is a parallel pathway that we are introducing. Okay, and this parallel pathway, it starts from the dimensions for that layer, input dimensions, and then projects it down to a smaller count of dimensions which we call r, which we also called rank, to a smaller rank, and then it projects it back up to the output dimensions. All right, so it starts from the input number of dimensions, it projects it down to a low rank dimensions, and then it projects it back up, and this is trainable. So this can undergo forward pass, back propagation, gradient computation, and optimization. Everything happens via this path, while this path is completely frozen. Okay, once this training happens, and at the end of this, it just adds whatever it has learned to the output of this layer. So that is what low rank adaptation does in a gist. But this is a very good paper, and I highly recommend reading through this. The core idea is extremely simple, but the applications that this enables us are quite a lot. So low rank adaptation. Then there is also quantized low rank adaptation. Then there is parameter efficient adaptation. There are so many fun things that came out of low rank adaptation. All right. So I told you what the core idea of low rank adaptation is, but I want to ensure that you like clearly understand this. Let me just come back to my blog post and just walk you through how exactly low rank adaptation happens here. All right. So see, low rank adaptation freezes 8 billion base weights and trains lightweight adapters, achieving 32 times parameter reduction during fine tuning. Okay. Let me just show you this diagram. So I really like having these ASCII diagrams in my blog posts because they're easy to generate and they get the work done to explain it in a visual manner. So as you see here, so this is the 8 billion instruct model and these are all the layers of it. And all the layers are layer 1 is frozen, layer 2 is frozen, all the layers are frozen. And we select a specific block. Let's say here is the attention block that we're selecting. Instead of the attention block, for the specific layers which are frozen, so this is the frozen path of that layers, we have a parallel pathway passing through these layers. And for these parallel pathway which are not frozen, these are trainable. Okay, the input dimensions whichever are here, and then that is projected down to our dimensions, and then it is projected back up to whatever the output dimension is from here, right? And then this is added back to whatever the frozen weight should have been there. If you see this is like weights which were frozen, and then this is matrix B, which in this terminology, while you're projecting it down, we call it matrix B, and when you're projecting it back up, we call it matrix A, right? Then there is a cross matrix multiplication for B cross A, and that is the output dimensions. Okay, so this is the frozen path and this is the learnable path, and this is only applied to very specific chosen layers. And in transformer architecture based models, these chosen layers are often a part of the attention block, which correspond to the query projections, key projections, value projections. All right, so I can also just show you with an example, right? So here, as we have seen in the yida classifier, while you are seeing this adaptation, low rank adaptation adapters, you notice this is the self-attention block of this model. You see inside of the self-attention block, there are K meaning key projections, query projections, you have value projections. And for these between, you notice here, for the key projection, which is the base layer, which is in BrainFloat 16, which is the original layer which it exists. And this has a parallel pathway, if you notice here, which is like low rank adaptation adapter pathway, which is in floating point 32. Then it has a low rank adaptation B. This is the matrix, which is like projecting this to a lower dimension and then projecting it back up to the higher dimension. Okay, see, just closely look at the shapes of this, right? So here it was initially 1024 to 4096 feature dimensions, and then this is projecting down to 16 rank, and then it is projecting back up to 1024. So this is the trainable low rank adaptation adapter here. All right, similarly you can also notice the same thing for your query projection as well. You see, this is the base which originally existed, which is frozen, and then this is projected down to just 16 rank, again 4096 feature dimension, and then it is projected back up to 4096 to 16. All right, so at the end of it again comes back to the original one that it had, which is 1024 to 4096. Okay, so this was a very practical real example of how low rank adaptation adapters are inside of the model architecture for a transformer based model. In this case, it is a Llama model. Inside of that, in the attention block, you are able to very clearly see that low rank adaptation adapters are between the key projections, query projections, and value projections. All right. So that is about low rank adaptation. Yeah, mostly that is about low rank adaptation. I hope you have understood somewhat about low rank adaptation, but I agree that this requires a lot of mental, mathematical intuition to completely get used to thinking in terms of low rank adaptation adapters. So again, I highly encourage you to read through my blog post, read through the research paper, go through some of the code, and try to build the mathematical intuition and try to get into the architectures of these different transformer based models and see how you would attach low rank adaptation adapters in different layers and how these low rank adaptation adapters specifically learn and add their learnings to the output from that layer, right? While all the other layers weights are frozen. So essentially, when these specific parallel pathways, you are passing some training through these pathways, you are forcing the model to learn based on just these specific parallel pathways, right? So for example, when you are trying to run mass next token prediction for LLM2Vec, you are using some high quality data set, which is passing for the training through the entire model, which is frozen, but only these specific models in the query projection, key projection, value projection, which it can effectively learn from this. It can do the forward pass, it can do the gradient calculation, it can go do the backward pass, and again it can move forward with the optimizers. So this entire loop happens only in these training layers while all the other layers are frozen. So just based on the learnings of these training layers, all of the fine-tuning data set that you are passing through this mass next token prediction gets learned, right? I understand this could be a little heavy to understand, but genuinely wrestle through these ideas and truly understand how low rank adaptation works, because it is going to be really useful and crucial for any kind of inferencing that you're going to do in the future as well. So yeah, that is low rank adaptation adapters right there. Let me come back to the code. All right. So yeah, again, you notice that max length is 512. It is just that you want to have consistent shape of the output, right? So that the linear layer can easily be attached. This is where we are attaching the linear layer, which is working as a classification head for layers. All right. So we have all the model loaded. So a quick walkthrough of what we have done so far. We just ensured everything, the memory is clear, no unwanted things are there. We loaded the base model, which is LLM2Vec Meta Llama 38 billion instruct mass next token prediction. Then we loaded the tokenizer. Then we loaded the base model, which is this model again, Llama T8B instruct MNTP LLM2Vec model. And to this specific model, we ensured that it is loaded onto our GPU. We do not want to move it from CPU to video, from RAM to video RAM, just unwanted bottleneck. So we're directly loading it on video RAM. And then for this thing, we are specifically loading the safe model or safe tensors that we got from LLM2 LLM Idiosyncrasies paper, which Yida released. We loaded our base model with these weights, and once we loaded that with those weights, we converted that into LLM2Vec with mean pooling so that we can attach its classifier head. Then we loaded the classifier head, initially randomly initialized, and then you loaded the head weights that you got from, again, Yida's classifier model that they released on huggingface. And then you are ensuring that this model is in eval state. You don't want any of the gradient computations to just form an unwanted overhead. You don't want to train it or learn from this, you just want to inference it. And then you're again ensuring everything is cleared out. Then you're returning the model, and then you have loaded the model. So now that we have our model loaded, now essentially we just have to run the inferencing of it, right? You just have to predict, pass through it and predict it. So how do you predict it? So the hard part we have already done. Now the easier part is just to run the predictions, right? So, so now you just sign what the predict labels have to predict it. You just take the model, which the model we already have above, and then you pass the text to it and this. Then you prepare the text, whichever the text you have, you prepare the text for tokenization, right? So now this model, whatever the model is here, this is the LLM2Vec model. LLM2Vec provides you with the method prepare for tokenization. The text is prepared for tokenization at this stage. Any kind of extra padding has to be added, or whatever kinds of things have to be taken care of. Everything's taken care of here, and then you're just tokenizing it for this prepared text that we got from here, that you're passing here, and you are just tokenizing that prepared text. And be sure that this is inside of square brackets, because that is what model.tokenize for LLM2Vec model expects. And then you just want to ensure that the device is appropriate, and then for on that specific device you give all of your inputs, which are of the type torch.tensor. Okay. So I hope you understand this dictionary comprehension here. It is very simple only. The thing is, for kv in the input.items, whichever the input dot items you have got from here, right, which is like tokenized text, for any of the input dot items, you want to check if these are the instances of torch.tensor. If the value is a torch.tensor input, you want to move it to your specific device, right? So the only reason is that all the tensors which you have, you want it to be on the same device. We are repeating this quite a bunch of times because this is a very common um, mistake that happens. Vectors tensors are on different devices and your entire computation gets flawed. And once you have that, you run the inferencing. You just ensure that you have no grad. We don't want any gradient computations here. And then you model.forward, you put all of your inputs. Inputs are again what? Just the tokenized text, which is on the device. Tokenized text which is on the device, which passes through the model forward pass. Okay. Now be very sure to understand this, that when it is passing through the forward pass, the head is not attached here. Okay, so head, if you notice, head is attached as an attribute. So model.head is attached as an attribute. It's just a regular Python object class attribute. So it is attached as an attribute. It is not passed into the forward method of this object, right? So when you are running the forward pass, only the initial whatever the layers were in the forward pass that are included here. So the model.forward pass gets the input, and once the LLM2Vec output come out of that model pass. So let me again go back to this diagram. So in the forward pass, all of these layers are a part of the forward pass, but this head is not a part of the forward pass. Okay? Because this head is an attribute. This head that you have here, this head is an attribute. It is not a part of the forward pass. So we have to explicitly pass it through the forward pass. So you are just saying if the model has an attribute, which is head, then whatever the embeddings that you got at this level, pass those embeddings through the head. Okay, to get the final embeddings. Okay, and whatever the embeddings you have, you want to convert that into brainport 16, and you apply the softmax so that these logics gets converted into probabilities. Okay, so once you have the probabilities, you can just index the probabilities and display it in the nicer way. All right, so now once this is done, we can just run our predictions, right? So this is a small example which we will use to run our prediction, and yeah, perfect. We have a prediction. This text is most likely to be from ChatGPT. Yeah. So we have it. So yeah, there we go. We have finished implementing the inference for this, and the only next step to complete is just having a Gradio UI to make use of this. Okay. And honestly, there is nothing to learn about how to build Gradio UIs. Mostly, whenever you have to build a quick UI for Gradio, I would highly recommend you to just use your cursor or whichever the coding platform that you're using, Claude, Code, or anything. Just ready to wrap it around a Gradio UI so that you can just share it with other people. So this is just a generated Gradio UI code, which also makes use of Plotly. Let me just run this code. So as soon as you run that, you get a link which you can access where the UI is present. Okay. Now that we completely implemented this on this video live, let's just test if this works. Yes. So where is my Safari? Here is the Safari. Let me just open it. It's not opening in Safari. Once I can just copy this specific part. So right here, our radio UI for this project is loading up. And as soon as this loads up, we should be able to find out. Okay, so this was what I showed in the demo video that I posted on Twitter as well. And we have in this video generated the entire thing. Right? What I'm going to do is I'm just going to get some text from Grok and test it out here, right? You don't show all of these things. Teach, what do you want to teach? Teach pragmatic probability Nanda. So, okay, just run this query. Let's wait for Grok to come up with a response. Yeah, once Grok comes up with a response, we are going to run the response through our newly built inference engine, which identifies which LLM generated. And let's see if it can identify that it is Grok which have generated this text. All right. Now the Grok is crafting an answer. This is also a good read about pragmatic intelligence. And if you're up to speed, you would know that Neil Nanda, who leads the mechanistic interpretability team at Google DeepMind, has recently shared his thoughts about how he wants to focus more on pragmatic interpretation. Yeah, so we have this here, and we are going to just paste it here. Let's just pray that it identifies that this is Grok. Oh yeah, it identifies that it is Grok, but with a rather less confidence of 31%. And the closest next is Claude with 30% and ChatGPT. Okay, but a good point, it just identifies that is Grok. Okay, so this also has a very interesting implication, right? So when this model was trained, or that Yida has trained this model, this was like a few months back. Then this was able to achieve 97% accuracy, and it was able to distinctly identify the idiosyncratic patterns. And now when we see that these distinctions are not that it should have like essentially shown this with like over 80% confidence, but it's just saying this 31% confidence, right? This essentially indicates towards one specific implication that might have happened in the past 6 to 7 months, 8 months, that these models patterns, the idiosyncratic patterns based on the newer models which are coming up, and because now this have used this research and this expert mode, so these are in some way aligning more with specific models, or these idiosyncratic patterns are in itself evolving with new models, new reinforcement learning methodologies being used, new supervised fine-tuning methodologies being used, new dataset classification guidelines given to the human labelers. All of these things combine, and this could be an evolving way in which idiosyncratic patterns can be seen in the future. right? So that is one indication why the results are so close to each other that I can think of, right? And also this also forces you to think that is there a need for a real time week wise, like 3 days wise evaluation of these idiosyncratic patterns in real time, so there are always up to date classifiers like this one, right? So is there a need for that? Is there a useful use case that we can identify to have such a real time LLM idiosyncrasies detection platform, right? There could be a lot of use cases for this. There could not be any major use cases out of this, but I'm really interested in understanding this. If I'm able to find out some very interesting use case and spin out a company out of this real time detection of which LLM generated which content, it will be a really interesting thing to build and work on. Yeah, if you think this could be interesting, or if there is a requirement of this sort which could eventually find some good use cases, feel free. We can talk about it and see where it goes. Yeah. So we have gotten to this stage, but we are not done yet. Okay. Uh, I want to explain few things to you here. This is the yidas thing, right? What we essentially did is we just loaded this model.save tensors, which already had all the adapters and everything attached and all the weights already loaded. This was the easier way of doing it. There could be a harder way of doing it, the more educational way of doing it, where we can just take a base llama model, and to that base llama model you attach your low rank adaptation adapters for mass next token prediction, for supervised contrastive learning sentence embeddings, right? And then you attach the head, and then you load the weights on head. So this could be more different modules you're taking from different places, assembling it and then running it. That is the more advanced way of implementing this and more educational way of implementing this. Outcome is essentially the same, but that enables you to think from the perspective of taking a llama model separately, taking adapters separately, loading the adapters onto the llama model, uploading the trained weights onto it, and then attaching the head and then running inference to all of this, right? That is the more educational way and more exciting way of doing this. Okay. So let me just quickly implement that as well. Let's do this. Okay. So this time, because we have already walked through all of this, it is going to be a little faster, I suppose. So let's just create a new file. Let's call it demo. Let's call it low bandwidth. The reason we'll call it low bandwidth is that we're not going to use the entire premerged model, right? We're just going to use specifics that we need, the adapters and everything. So let me just spin this up. And for the time being, I'll just pause this because I already ran through all of this and it is working pretty well. We know that. We'll interrupt this and let me just close it all together. Okay, just save it. It doesn't matter. We are going to turn off this instance anyways. So we are coming to code. So I already have a notebook and I also showed you the repo. What I'm going to do is I'm just going to run the snippets from my repo here one by one, and let us just see how this works. Okay, I'm just going to fast run through this all implementation. I just don't want to leave any stone unturned in the educational value that we can grasp from this, because we're already in the zone. We have come so far. There's just small tweaks which would just make it even more better. So why not just do that? So we just select our kernel, and now okay, it is connected. We just run all the things one by one quickly. We ran this. We are going to restart it. So essentially, I just downloaded our these things here, and then let's just ensure that we have the right dependencies, because I want to be very particular about this, because I told you that if these dependencies are not in sync, you can waste a lot of time and a lot of cognitive load without any concrete progress. So we have verified all the version checks got passed, and then you are just downloading the model, just so that everything is there. It won't download it again, of course, because it will be cached in the volume. And then you want to just clear all the cache. And then here is the big important load classifier. I'll just run it for now, and I'll walk you through what exactly we are doing here in the next step. And then after this load classifier thing is done, rest of the things remain same, which is the predict text, and then this, and then just a small demo of that, and you can just end it with your Gradio UI. All right, so that remains. All right, the model has been loaded here, and this time the model is not a premerged model that we got from yidas. This time the model is what we built from the adapters that we assembled. I'll walk you through this code. In the meanwhile, I just want to run this and just ensure that everything works. So yeah, the predictor works, and successfully the prediction also is working here. And then also the Gradio UI, which you can just generate, and the Gradio UI also is working here. Perfect. So this time we have essentially achieved the same outcome, but we have done this in low bandwidth mode by assembling all the bare parts ourselves. All right, so now if you see this closely, what we're doing is earlier we just took the base model. Now we are taking the base model, which is Meta Llama 3 8 billion instruct. Then you're taking the mass next token prediction adapter. Okay, so I'll just quickly show what all of these models are. This is the base model that you have here. This is the base model. This is the heavy weight model that we have. These are all the tensors. What is the original one? This is the original. If you see, this is Llama 38B instruct model, which was released by Meta Llama. This is the original model that got released that we are using as the base model. And then we are using the MNTP adapter ID, which we are going to use to load the low rank adaptation adapters for mass next token predictor. This we are going to load directly from the model that we previously also I showed you, this model. And this, if you see, there are like specific adaptation configs, right? Here you're able to see what are the adapter config.json. So in this adapter config.json, you are able to see all the things specifically mentioned here. Like what are the inference mode and what are the low rank adaptation alpha. All right, if you actually look into the low rank adaptation mathematical formulas, you will come across things like alpha and dropout. I would encourage you to read upon this once. Not so complex, but just mathematically, you want to ensure that the low rank adaptation adapters learn efficiently and learn in a ratio with other layers, which makes sense, and the learning is most optimal. So those some of the parameters are there, and on which specific layers you want to implement low rank adaptation adapters. As I told, it's like query projection, gate projection, down projection, up projection, value projection, O projection, key projection. These are the specific layers where you want to implement your low rank adaptation adapters. So these are all the files that you have here in this. Oh, yeah. Uh, in this here, these are the config of that, and these are all the. If you see, these are adapter model safe tensors you have, right? This is just 168 MB in size, and this has all the adapters for along with which layer applies which adapter to. So this I have given here so that we can get access to the adapters, and then I have given here for the supervised MNTP supervised as well, which adapters you want to use for that. So that is this model. And even if you see here for this model, you will see there are adapter config and adapter model safe tenses which we have available here. All right. So these are all the raw ingredients which we are going to use to construct our model. Okay, so first we are loading the tokenizer just like before. And then for the, okay, this is an interesting thing. For the tokenizer, you want to be specific about the padding, right? LLM2Vec padding has to be very consistent. So LLM2Vec essentially looks at the final layers of it. It has a convention that all the padding should be on the left side, right? Padding is essentially whatever the maximum size, which in our case is like 512 tokens or sequence length that we have decided, that anything less than that should be padded. So all the padding tokens has to be on the left side. So once you have the padding tokens on the left side, you are loading the base model. See, specifically, you are loading the config for the base model ID, which is the Llama model, which is originally released by Meta. That config you are loading. Based on that, you are also using your base model. You are loading the model itself here, right? Once you have loaded the base model, here is the interesting thing. Once you have got the base model loaded, then you are attaching your first adapter. Okay, this first adapter is your mask next token prediction adapter. All right, where are you loading this adapter from? mntp adapter id, which corresponds to, as I told, this, right? This, which is this. So this config is being used directly for attaching, merging mask next token adapter here. Okay, so this adapter, if you notice, it is using parameter efficient fine tuning model. What is parameter efficient fine tuning model? For LoRa adaptation adapters, what you can, this is the library that the industry defaults onto, parameter efficient fine tuning model. So this is very good. See, it has like 20,000 stars, which itself is a good indication about how useful and industry wide this is used. What I'll do is I'll just show you the library. This is PEPT, parameter efficient fine tuning. There is a newer version available. Yep, show me the newer version. Once you have this installed, so it gives you access to a lot of parameter efficient models based on which you can apply your low rank adaptation and other kinds of parameter efficient fine tuning methodologies. Like low rank adaptation adapter is one way of doing it, right? So in model set adapters, you can adapt and set low rank adaptation adapter 2 and all of these things. It's like a very good one. You can go through the code also and run through the examples that they have here, right? So that you get a like very close understanding. So usually that's how you learn about any new library and anything. You just run the examples and see, and then you read the docs of that specific library. See, you understand. See, low rank adaptation adapter methods are here. Prompt based methods are here. So you'll have a complete picture of what parameter efficient fine tuning enables you to do. Okay, you have quantization, you have mixed adapter types. So this is like a very good library. So I encourage you to read this. And here we are using the same library so that we can use our low rank adaptation adapters for MNTP adapter. Right, that is loaded onto our model. And that is the first adapter that we have loaded onto the model. And once we adapted loaded onto the model, you have to ensure that you have merge and unload. Once you merge it, those adapters weights are merged, and then the specific parallel pathways that got attached, those pathways get removed. Okay, so just only the weights are attached and the parallel pathways which are no longer needed anyways, those are removed. Okay, then you are just clearing any of the caches or anything, then you are attaching your next adapter, which is supervised adapter. Again, this is the adapter ID, which as I told is here, the specific models adapters from the adapter config, you will get it. And yeah, again, we load that adapter. It is essential that you clear the unload the previous adapter so that the new adapter can be attached and they don't conflict with each other. All right, then you ensure that the padding is on the left. As I told earlier as well, the padding has to be on the left for LLM2Vec to work properly. And then wrap the entire model on LLM2Vec, same mean pooling, max length, all of that. And again, verify the tokenizer is properly set up, and then you are adding the classification head on top of it. Then to the classification head, you are loading the classification head with the actual weights that we want it to have. Then again, model eval, you are returning the model. That's it. Right? That was like pretty simple, right? You are just, the only change that essentially happened is that you loaded the base llama model which got released by Meta, and then to that you attached your adapter, mntp adapter, and then to that you attached your supervised adapter id. Okay, and you can attach the adapters and run your own training as well on this if you feel like. But yeah, that is the methodology using which you can do this. Okay, so that was it. That is how the project went through. I hope it was a fun learning experience if you followed along till the end of this video, which is what, 2 hours 20 minutes, which is a very long time. So I thank you from the bottom of my heart to follow along with such a long video. And if you found this educational, or if you learned anything new from this video, please write to me. I would love to hear more. And yeah, thank you. If I make a next video, if you would like to watch videos like this, please encourage me. And yeah, thank you. See you. Bye bye.